In the last lecture, we laid the topological framework to state Cauchy's theorem. Cauchy's theorem basically states that if f is a holomorphic function, then the integral of f over a rectifiable curve is homotopy invariant. Let me write down the statement. Cauchy's theorem. Let's work on an open subset omega of C. Let omega contained in C be open and f from omega to C be holomorphic on omega. If gamma 0 from AB to omega and gamma 1 from CD to omega, they are two rectifiable curves. Say they are rectifiable curves from Z0 to Z1. We are imposing the condition that both gamma 0 and gamma 1 have the same initial point Z0 and the same terminal point Z1, and that they are rectifiable curves, and such that gamma 0 is homotopic with fixed endpoints to a reparameterization of gamma 1. And suppose gamma 0 is homotopic to a reparameterization of gamma 1, then the integral of f over gamma 0, this is the same as the integral of f over gamma 1. This is what it means to say that the integral of f is homotopy invariant. We go from one curve to another curve to which the given curve is homotopic with fixed endpoints, then the integral is going to be preserved. Not just about homotopy with fixed endpoints, this is the case with homotopy as closed curves as well. So let me write that down as well. If gamma 0 from AB to omega and gamma 1 from CD to omega are closed rectifiable curves, such that gamma 0 is homotopic as closed curves to a reparameterization of gamma 1. Of gamma 1, then the integral of f over gamma 0 is the same as the integral of f over gamma 1. The Cauchy's theorem is a very powerful tool in the sense that it can be used to compute the integral of f over any rectifiable curve by shifting the curve via homotopy to a contour over which the integral can be computed easily. So this makes the computation of integrals in many cases far easier. We will now state a variant of the Cauchy's theorem. It essentially says the same. Let me just call it as Cauchy's theorem 2, and then we will see that it is going to be equivalent to what we have just written down. Cauchy's theorem, the variant states the following. Again, let omega be open and f be a function which is holomorphic on omega. Suppose gamma 0 from AB to omega is a rectifiable curve which is null homotopic. Recall that a curve is said to be null homotopic if it is homotopic as closed curves to the constant curve based at the starting point of gamma 0. That means there is a homotopy from gamma 0 to gamma 1. Gamma 1 is a map from AB into omega defined by gamma 1 of t is equal to z0 for all t in AB. And z0 is such that it is the initial and terminal point of gamma 0. So suppose gamma 0 is a rectifiable curve which satisfies this condition. It's null homotopic. Then the conclusion tells us that integral of f of z dz over gamma 0 is equal to 0. Let's compare the two variants of Cauchy's theorem. This tells us that if we have two curves which are homotopic to each other, then the integral is preserved. Now assume that gamma 1 in the case above, say for example in this case gamma 1 is the constant curve. We know that the integral of f over a constant curve is 0, and by using the part 2 of the first version of Cauchy's theorem, we can immediately conclude that Cauchy's theorem 2 is satisfied, because we know that this is equal to the integral over gamma 1 of f of z dz, which is equal to 0 because gamma 1 is a constant curve. The more complicated, or rather it's not complicated, the non-trivial part, let me put it that way, it's to show that the converse is true. So maybe I should write down another proposition here. Cauchy's theorem 2 implies Cauchy's theorem. The other side we have already easily checked. So this is the final step in the direction of establishing that the two variants that have been written above both are equivalent. Alright, let's try to prove the variant, the part 1 here. I will leave the second part as an exercise for you. So let gamma 0 and gamma 1 be curves which are homotopic with fixed endpoints. So let me use, without loss of generality, the domain of definition of gamma 1 to be equal to AB itself, because otherwise we could just reparameterize it and realize it as a curve on AB. The integral doesn't change when we do a reparameterization. So we may as well start off with gamma 1 defined on AB, such that gamma 0 is homotopic to gamma 1 as fixed endpoints. Then homotopic with fixed endpoints. And if you notice, gamma 0 plus the reversal of gamma 1 by one of the exercises given in the previous lecture, this is homotopic to gamma 1 plus minus of gamma 1. We have used actually more than one exercise from the previous lecture. The first one is to say that it is indeed reflexive. Minus gamma 1 is homotopic to minus gamma 1 itself. And if gamma 0 is homotopic to gamma 1 and minus gamma 1 is homotopic to minus gamma 1, then gamma 0 plus minus gamma 1 is homotopic to gamma 1 plus minus gamma 1 with fixed endpoints, of course. And by using one more property from the previous lectures, gamma 1 plus minus gamma 1 is homotopic to the constant path, which let me call it as gamma 2 with fixed endpoints, where gamma 2 of any point t is just the point z0, which is the same as gamma 0 of A. And now let's use the Cauchy's theorem, the second variant of Cauchy's theorem, which helps us conclude that integral of f over any closed rectifiable curve is 0 if the curve is null homotopic. We have just established that the curve gamma 1 plus minus gamma 0 plus minus gamma 1 is homotopic to a constant path and hence null homotopic. by Cauchy's theorem 2, we have integral of f of z dz over gamma 0 plus minus of gamma 1 is equal to 0. And I'll just leave it to you. I think we have done enough of these manipulations to conclude that this is the same as demanding that this is if and only if f of z dz over gamma 0 is equal to integral of f of z dz over gamma 1. A very similar proof can be used to conclude the second part of the Cauchy's theorem which we stated initially. So these two statements therefore are logically equivalent. In both these cases though, one thing to keep in mind is that we have demanded our function f to be holomorphic on the entire open set omega. We are not restricting our attention to how f is defined in a neighborhood of gamma 0 and gamma 1, even though we are only considering the integral of f along gamma 0 or gamma 1, we are still demanding that our function f here is holomorphic on the entire space omega. So this can be explained by observing that the curves gamma 0 and gamma 1 are homotopic to each other, and for homotopy to exist between gamma 0 and gamma 1, our domain omega should be sufficiently large, and our function f should also be holomorphic on such a sufficiently large domain. So that's an idea which is best illustrated by the following example, or rather non-example. If you look at the function f of z is equal to 1 by z, that's a function which is defined on omega given by c minus 0. So our domain here is c minus 0, and consider our curve gamma of t to be equal to e to the power I t for t belonging to 0 comma 2 pi. Suppose we have our curve defined on this particular interval. Then we have already checked that the integral of f of z dz over gamma, this is equal to 2 pi I times I. So we have a closed rectifiable curve on which the integral of f is not equal to 0. Cauchy's theorem would demand that such a curve such a curve not be null homotopic, because if gamma was null homotopic, if it was homotoped to a point, then Cauchy's theorem would have forced this to be 0. So gamma is not a curve which can be homotoped to a point. The reason is quite straightforward. We have the origin here in the complex plane where our function f is not holomorphic, and therefore the origin does not belong to the domain of definition, and the absence of origin ensures that our curve gamma cannot be homotoped to a point. So this in particular illustrates that the property of f being holomorphic on the space omega, the global nature of such a demand is requisite for the conclusion of Cauchy's theorem here. Okay, let's get down to proving Cauchy's theorem. As a first step, we will be proving Cauchy's theorem on a special case. The case when our curve gamma is a triangle. It's a polygonal path consisting of 3 sides, such that the convex hull is contained in our given domain omega. And we will prove this. This version is called Gursas theorem, and Gursas theorem will be applied or used to prove the more general Cauchy's theorem. Let me state the Gursas theorem and we will then prove it. Suppose omega is a domain in C, f from omega to C be holomorphic, and z1, z2, z3 be 3 points in omega, such that the convex hull of z1, z2, z3 is contained in omega. That means that summation ai zi or a1 z1 plus a2 z2 plus a3 z3 belongs to omega whenever summation ai is less than or equal to 1 is contained in omega. Then consider the polygonal path consisting of straight lines joining z1 to z2, z2 to z3 and z3 to z1. If you consider this polygonal path, f of z dz is equal to 0. So why is this being treated as a special case of Cauchy's theorem? Because the fact that z1, z2, z3 are points whose convex hull is contained in omega effectively tells us that the curve gamma z1, z2, z1 to z2 to z3 to z1, that is a null homotopic curve. And we are demanding that the second variant which was written above, which was logically equivalent to the first variant that we wrote, that will be satisfied by this particular statement. So we are doing it for very special curves, and that is why it was mentioned that a special case of Cauchy's theorem is being proved. So let me give a proof of the Gursas theorem. We will prove it first by drawing an image of the setup we are in. So we are in a domain. Again, need not be this good at domain, but we certainly have a triangle of this type. There is z0, z1, or maybe z1, z2, z3. That's what it's used. z1, z2, and z3. Such that the convex hull is also, this is the convex hull if you notice. This is also contained in our given domain omega. And the curve gamma is the straight line path z1 to z2 concatenated with z2 to z3, which is then concatenated with z3 to z1. Let's do one thing. Let's give the curve a compact notation. Let us denote the curve gamma z0 to z1 to z2 to z3 to z1, this curve by t0. Let's denote this curve by t0. We will prove that we'll prove this theorem by contradiction. We'll prove that if this integral is not equal to 0, we'll come to some contradiction. What does it mean to say that the integral is not equal to 0? Suppose integral of f of z dz over t0, this is not 0. That means the absolute value will be greater than some epsilon for some epsilon positive. Now let's come back to our image here. Let's give some names to the midpoints. Let the midpoint here be z12, let the midpoint here be z23, and the midpoint here be z31. And let's join these lines. So I kind of threw out the orientation. This was the orientation of the curves. Right. So the orientation here would be like this. So notice that the integral of f over gamma, which is the polygonal path joining z1, z2, z3, if we somehow bring in z12, z23 and z31, we can split the integral, and after some calculations we can conclude the following. Then integral of f of z dz over t0, this is equal to the integral over gamma 1 of f of z dz plus integral over gamma 2 over gamma 3 and over gamma 4. So what are these gamma 1, gamma 2, gamma 3 and gamma 4? So this is gamma 1, this is gamma 2, this is gamma 3, and this is gamma 4. Notice that there will be cancellations of these triangle to get back integral of f over t0. Let me write down what gamma 1 is, where gamma 1 is the curve z1 to z12 to z23 or z31 to z1. Gamma 2 is gamma z2 to z23 to z12 to z2. Gamma 3 is the curve gamma z3 to z31 to z23 to z3. And gamma 4, this is just gamma z12 to z23 to z31 to z12. So we have captured the 4 triangles, and by noting that there will be cancellations on the sides of the red triangle, we will be able to conclude that the integral of f over t0 is the same as this, as the thing on the right. And by triangle inequality, we have this is the same as this, which is less than or equal to the absolute value of the individuals. So let me just write that down. Integral of f of z dz over t0 absolute value. This is less than or equal to integral over gamma 1 of f of z dz absolute value plus dot 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 plus absolute value of integral of f of z dz over gamma 4. But we also know, or rather we have assumed, that integral of f over t0 that is greater than or equal to an epsilon positive, and hence there exists a curve, hence there exists one of gamma 1, gamma 2, gamma 3 and gamma 4, one of those 4, which will denote by t1. Such that integral of f of z dz over t1, the absolute value, is greater than or equal to epsilon by 4. So let me just go up and show you what is being written here. There are 4 terms which are featuring in here. The sum of these 4 terms is greater than or equal to epsilon. All are positive, so at least one of them is necessarily greater than or equal to epsilon by 4. That is what is being said here. That's forced because if all of them are less than epsilon by 4, their sum would also be less than epsilon by 4, and this would be contradicted. So one of them will certainly be greater than or equal to epsilon by 4. It doesn't matter which one, let's pick one of them, one of gamma 1, gamma 2, gamma 3, gamma 4. So it's going to be one of these 4 triangles that are drawn here, which will be denoted by t1, and which satisfies the condition that integral of f over t1 is greater than or equal to epsilon by 4. The thing to note here is that the diameter, note that, before I come to the diameter, the arc length of t1, this is just going to be equal to arc length of t0 by 2. And also the diameter of t1 is just the supremum of mod of z minus w, where z comma w belongs to t1, or the image of t1 rather. This is going to be equal to the diameter of t0 by 2 again. So remember that this is the supremum of absolute value of z minus w, where z comma w belongs to t1. Let me just put it that way. This means that it is in the image of t1. t1 is a curve after all, right? So it's the supremum of the differences there, and that's always going to be that will be less than or equal to, or in fact here it will be equal to the diameter of t0 by 2. You should sit down and check both these statements here. Now we will do an exact same procedure on T1 as well by repeating the process above. I will not write it down in detail. Process above, we get T0, T1, T2, so on, such that the integral of f of z dz over Tn, this is greater than or equal to epsilon by 4 to the power n. So at every stage it's going to be greater than epsilon by 4, and therefore at the nth stage 1 by 4 term is being multiplied at every stage. So this is going to be greater than or equal to epsilon by 4 to the power n. Okay, we are in good shape as of now, because if you notice, diameter of Tn, this is just going to be equal to diameter of T0 by 2 to the power n, which converges to 0 as n goes to infinity. So pick some Zn. Oh, in fact, notice that we can say more here. We can say that diameter of T1 hat is equal to diameter of T0 hat by 2, where T1 hat is the convex hull of T1 and T0 hat is the convex hull of T0. So let's just go up to the figure and again look at what the convex hull of T0 will be. The convex hull of T0 is going to be this entire space inside the bigger triangle, and the convex hull of T1 will be the entire space inside the smaller triangle. And the convex hull of T0, as you can see, contains the convex hull of T1. It can be checked rigorously by writing down the details, and at every stage we can say the same thing here. You can say that the diameter of Tn is equal to diameter of Tn hat rather is equal to diameter of Tn minus 1 hat by 2, which inductively will hence be equal to diameter of T0 hat by 2 to the power n. Diameter of T0 hat is a constant value and this converges to 0. Now pick some Zn which belongs to Tn hat, and notice that this sequence and by star, so this is by the previous observation, let me not call it anything, by the previous observation the sequence Zn turns out to be a Cauchy sequence, because remember that the convex hull Tn hat is sitting inside the convex hull Tn minus 1 hat. So it's a decreasing sequence of sets, and therefore this is certainly a Cauchy sequence which has a limit because of completeness of omega by completeness. Zn converges to some point, let's call it Z0. Z0 will be certainly in each of the Tn's. In particular, it's going to be in the intersection of Tn's. So hence it's going to be in omega. So no problem there. And because Z0 is in omega, we know that our function f is holomorphic at Z0. Till now, if you notice, we have not used any of the holomorphicity properties of f. We have just been using the fact that there are some nice properties of the integrals which can be used to concentrate our integral onto smaller and smaller places and give bounds on that. So remember that this is the bound we have always had till now. Now on the point Z0, let's use the fact that f is holomorphic, complex differentiable. Since f is complex differentiable on omega, since f is complex differentiable in particular at Z0, given epsilon positive, there x is a delta positive, given epsilon prime positive, we have already taken epsilon, given epsilon prime positive, there x is a delta positive such that the absolute value of f of z minus f of Z0, this minus f prime at Z0 times z minus Z0, this is less than epsilon prime times z minus Z0. This is by just clearing out the denominators in the Newtonian quotients. Whenever absolute value of z minus z0 is less than delta. This is something which we can certainly say from the complex differentiability of f at z0. And notice that for large n, because the diameter of Tn is converging down to 0 and z0 is in each of these Tn's, Tn hat is contained in dz0 delta, and therefore hence mod of z minus z0, this is going to be less than the diameter of Tn, which is equal to the diameter of T0 by 2 to the power n. Notice that this is all possible because Tn hat is contained in the ball of radius delta around, disk of radius delta around z0. Okay, so what do we have? Hence, i.e., the absolute value of f of z minus f of z0 minus f prime at z0 times z minus z0. This is less than epsilon prime times the diameter of T0 by 2 to the power n. So, in particular, if we are to consider the absolute value of the integral of f of z minus, so let me split it and write it down carefully. This is f of z0 plus f prime at z0 times z minus z0. This absolute value, the integral is for the entire thing dz. This is less than or equal to the bound epsilon prime into diameter of T0 by 2 to the power n times the arc length. So over Tn is going to be bounded by the arc length of Tn. And we know precisely what this is. This is exactly equal to epsilon prime into the arc length of T0 into the diameter of T0 by 4 to the power n. By the previous, one of the previous observations, I have already noted that the arc length also goes down by half at every stage. So here, parallelly, we could also note that the arc length of Tn is arc length of T0 by 2 to the power n, because arc length of Tn is equal to arc length of Tn minus 1 by 2, yeah. So inductively we get hold of this. But then what is the thing inside the absolute value that we have written here? The absolute value splits up, or rather the integral splits up. This is going to be integral over Tn of f of z dz minus the integral over Tn of f of z0 plus f prime at z0 times z minus z0. This is exactly what is this thing inside the absolute value. And I will leave it to you to sit down and check that this integral vanish. The clue is to use the first fundamental theorem of calculus, and the fact that whatever is being integrated has an explicit antiderivative and that Tn is a closed curve. So by the first fundamental theorem of calculus, the first term vanishes, and hence we get to conclude that the integral of f of z dz over Tn, the absolute value is less than or equal to less than epsilon prime times the arc length of T0 into diameter of T0 hat by 4 to the power n. So if we had picked epsilon prime large enough, or rather small enough, so that epsilon prime times the arc length of T0 times the diameter of T0 hat is less than epsilon, then we can conclude then for epsilon prime small enough, we have the absolute value of f of z dz integral over Tn. This is less than epsilon by 4 to the power n. But how did we pick our Tn's? Let's go up and check how we had picked our Tn's. Tn's were inductively picked so that at every stage it is less than, or rather it's greater than epsilon by 4 to the power n. This is how T1 was picked, and by repeating the integral, the inductive process there, we had picked Tn in such a manner that integral of f of z dz over Tn has absolute value greater than or equal to epsilon by 4 to the power n. So let's call this star, and we have just concluded that for n large we can ensure that this is less than epsilon by 4 to the power n, which is a contradiction to star. So if we start with the assumption that our function f has an integral over t0 greater than or equal to epsilon for some epsilon positive, then we are arriving at some kind of a contradiction. And that means that our assumption has to be false. Thus, integral of f of z dz over t0, this is less than epsilon for all epsilon positive. In particular, this tells us that the integral of the absolute value, and this in particular tells us that the absolute value is equal to 0, and hence the integral itself is equal to 0. And that's precisely what we had set out before. This is an unusual proof by contradiction, which is not expected at first sight. So one thing to keep in mind is that the argument we have given here did not use anything more than the differentiability of f at the point z0. Of course, z0 was arbitrary, and therefore we do need that it could be any point in the domain, but we don't certainly demand that the function f is continuously differentiable. So that's something which you should keep in mind, because most of the results that we proved earlier, we did use somehow or the other the fact that, or the requirement that f be continuously differentiable. Here we did not use that. Let me conclude this lecture by giving a proof of the Cauchy's theorem on a very special case. We will prove the more general case in the next lecture. Here we will prove that if our curve gamma is polygonal and such that its convex hull is contained in the given domain. So let's start with a convex domain, for example, and if you consider any polygonal, closed polygonal path, then the integral of a holomorphic function f over the polygonal path is 0. So let me write it down, Cauchy's theorem. For polygonal paths. So let omega be a convex domain, and gamma z0 to z1 to all the way up to, say, we'll start with z1 itself, to zn to z1 be a closed polygonal path. Notice that this ensures that the convex hull is also contained in our given domain omega, because the domain omega is convex. And suppose f is a function defined on omega which is holomorphic. Then integral of f of z dz over the closed polygonal path this is not zn, this is z1, this is equal to 0. Let's give a proof of this. The proof is by induction. So let me just draw a picture for you so that the setup is clear. We have some domain and we have a point z1 to z2 to z3 right. So this is z1, z2 and so on. This is going to be zn minus 1, this is zn, and then finally back to z1. This is our setup, and because it's this is a convex domain, so I shouldn't be drawing it like this. Let me be more careful. This is something like this. Let's say this is our domain omega, the interior of it, and our domain is our curve is like this. We will prove it by induction. The proof is by induction. Well, n equal to 1 case, there is nothing to prove. It's just going to be a point. The polygonal path is just going to be a point. When n is equal to 2, yet again it's going to be gamma z1 to z2, but then it has to get back. It's a closed path, so z2 should necessarily hence be equal to z1. And because it's a straight line, it's just going to be again a constant path. So when n is equal to 1 and n is equal to 2, we are just looking at the integral of f over a constant curve. And there is nothing to prove there. It's already known to be equal to 0. For n equal to 3, Gauss's theorem we just proved establishes this. Tells us that integral of f of z dz over gamma is equal to 0, where gamma is the polygonal path, closed polygonal path. We will now put the induction hypothesis. Assume that the result is proved for up to n minus 1. And let's get back to our result here. Suppose we have this as our setup, and let's draw the straight line path joining z1 to zn minus 1. And by using the usual properties of the integral over polygonal paths. So all through I've used this crucially, that integral of gamma z1 to z2 to z2 to z3 to z3 to z1, that polygonal path, it's a polygonal path is a concatenation of straight lines. So we can split it up and write it as the sum of the integral over these straight lines. That has been used crucially all along. We will use that yet again. We will use that to conclude here. Then integral of f over gamma z1 to z2 to zn to z1, this is equal to the integral of gamma z1 to z2 to zn minus 1 to z1. So let's go up and see what we did. We went along these curves and then we went along zn minus 1 to zn. That's what we did. That is the curve being captured here. And then one more curve in the story would be gamma zn minus 1 to zn to z1 to zn minus 1. So basically zn minus 1 to zn minus 1 to zn to z1 and back to zn minus 1. Right? That's what is being captured here. Right. Of f of z dz. The integral along the line zn minus 1 to z1 is cancelled off each other by the straight lines appearing here and the straight lines appearing here, just like it had done in the previous case. Okay, now we are again good to go, because by induction hypothesis this vanishes by induction hypothesis, and this is going to vanish by Gauss's theorem. because here the convex hull is going to be inside our given domain omega, because omega is a convex set. This is by Gursa, and this is by induction hypothesis. Both vanish, and we get to conclude that hence the integral of f over gamma z1 all the way up to zn to z1, this is equal to 0. And that's precisely what we had set out to prove. In the next lecture, we will be proving the Cauchy's theorem in the manner we had stated in the beginning of this lecture.